Hello my dear friends, I am Shubham from LearnerHub, the free learning platform where you can study physics, chemistry, maths, biology absolutely for free at learnerhub.com. So then, let's start. So friends, in this video we are going to continue the next concepts, the remaining concepts of this chapter, periodic properties and variations in the properties physical and chemical. So far we have learned till the chemical reactivity and the physical properties, right? If you have followed the videos so far, if you haven't watched the previous two videos, please do watch those, because those videos would help you to build a basic build up of this chapter. Okay, now moving ahead, what we are going to learn in this chapter, we are going to see ionization energy, electron gain enthalpy or electron affinity, and electronegativity. These three periodic properties, and apart from that we are going to see some small concepts of diagonal relationship and the stable and the radioactive elements. Then we are going to solve some questions. So without wasting much time, let's start quickly and let's rock. Okay, now let's see what actually ionization energy means to us. Okay, very simple. You just try to understand this story. You would automatically remember as well the definition of ionization energy and understand as well. Okay, so this is an atom. Okay, we all know atoms are neutral. But what I did is I isolated this atom from all the other atoms. Okay, so this is all. So I can call it as an isolated atom, right? Now, suppose this is a sodium atom, okay. Now I know sodium exists in solid state, so sodium atom would also exist in solid state, right? So what I did, I separated the sodium atom from all other sodium atoms, okay, and then from the solid state I converted it into the gaseous state, okay. Now this atom is in the gaseous state, sodium atom, okay. So what I can say about this atom now? This is a neutral, isolated and gaseous atom. Now what I'm going to do is I'm going to remove the outermost electron from this atom. Okay, here it is. Okay, here somewhere the nucleus is. Now for removing this electron, I need energy. So yes, I need to provide the energy. Okay, fine. What happened? I provided the energy which is required to remove the electron, and the electron is now removed. Now what happened to the atom? We know when the sodium loses an electron, it would form an Na plus ion. Very clear. Because it has one electron less than the total number of protons. Okay, it would have 11 protons and 10 electrons. So one proton is more, so one positive charge. Now same way, it would form a Na plus ion. Okay, now this Na plus ion is a, we know, positively charged. Since the atom is in the gaseous state, ion would also be in the gaseous state, so positively charged gaseous ion. Very clear. Now what actually ionization energy is? It's very simple. This energy, okay, this energy which we are supplying, okay, or which is required to remove this very electron from the neutral isolated gaseous atom to convert into positively charged gaseous ion. This energy is called as ionization energy. Okay, very simple. Here you can see the definition. It exactly matches with what I said. Okay, the energy required to remove the electron, okay, from a neutral isolated gaseous atom, okay, neutral isolated gaseous atom, to convert it into positively charged gaseous ion. See, to convert it into positively charged gaseous ion. Okay, so this energy is called as ionization energy. Isn't it interesting? Okay, now we also call this energy by two different names. Okay, it is also called as ionization potential or ionization enthalpy as well. Okay, now we measure this ionization energy in some units. Okay, so the units are the normally used unit is electron volt per atom. Okay, and the SI unit which we use to measure the ionization energy is kilojoules per mole. Okay, now let's move on to the factors on which ionization energy depends. So we all know, apart from atomic size, I have already told you all the other periodic properties, okay, all the rest 5 periodic properties would depend on atomic size and nuclear charge. So here ionization energy also depends on atomic size and nuclear charge. So first we are going to see what happens to the ionization energy when atomic size increases, and then we would see what happens to the ionization energy when nuclear charge increases. Okay, so here let's see what happens to the ionization energy when atomic size increases. Okay, so I'm taking a very cute atom. This is the nucleus of the atom, first shell, second shell or outermost shell, and the electron, outermost electron. So it is being pulled by the nucleus with some attractive force. Then I'm increasing the size of the atom. Okay, now this is the outermost electron. This electron is also getting pulled by the nucleus with some attractive force. But the nuclear pull experienced by this electron, okay, is lesser as compared to this electron. Why? Because this electron is farther away from the nucleus. Okay, so it would pull with lesser attractive force. Now here, till here we know the story, but now what actually ionization energy is? To be put in very simple terms, what you have to just remember is ionization energy is simply the energy required to remove the electron from an atom. Okay, that's it. No need to remember the entire definition. Okay, for practical purposes, to just correlate the things, you can remember in this way. Okay, we have already seen the definition in detail as well. Okay, now what do you think? I'm giving you a scenario. If you are holding something, okay, very tightly, and I also want that thing. Okay, so what I would have to do now? I would have to pull that thing with so much energy to get that thing from you, right? But now if you are holding that thing very loosely, so if I would apply very less energy as well, that thing I would pull out from you. Okay, so same thing is happening here. Since here the electron is being held very strongly, so the energy required to remove this electron, okay, would be more than this case, than the case in which the electron is farther from the nucleus. Okay, because here it is farther. Since it is farther, it is being held with less force, so less energy is required. Okay, as compared to the first case. Okay, you can understand in either way. So now let's see this in this way. Okay, less energy is required to remove this electron as compared to the first case. Why? Because this electron is being held by the nucleus less strongly than the first case. Now less energy is required to remove the electron means the ionization energy in the second case is less. Okay, so suppose the ionization energy in the first case is suppose 20. Okay, I'm taking just a random number. Now what I told is the ionization energy in the second case is less than the first case. So in this case, if it is less, I'm taking 10. So what is happening? See, when I'm increasing the size, ionization energy is decreasing. Now let's see what happens to the ionization energy when nuclear charge increases. Okay, so this is the atom, outermost electron. Now this outermost electron is being pulled by the nucleus, okay, with some attractive force, we all know. Now what we would do is I would increase the nuclear charge. Okay, now increasing the nuclear charge, I'm just showing it in the pictorial form by increasing the size of the nucleus. It doesn't happen in the same way. Okay, now after increasing the nuclear charge, now the same electron would be pulled by the nucleus with more attractive force, strongly I mean. Okay, now what would happen? You only think logically. Just now we understood the thing that if the electron is more strongly held by the nucleus, more energy would be required to remove that electron. So the energy required to remove the electron in the second case, okay, the second case means the case in which the nuclear charge has increased. Okay, so in the second case, the energy required is more as compared to the first case. Okay, now what does this energy means to us? The energy required to remove an electron, ionization energy. So what I mean to say is the ionization energy, okay, in the second case, I'm just writing here 2, okay, is more than the ionization energy in the first case. The first case is having less nuclear charge, the second case is having more nuclear charge. So what it is indicating? When nuclear charge is increasing, okay, ionization energy is also increasing. Okay, because ionization energy in the second case is more than the first. So absolutely it is increasing. Okay. So now let's see the trends of the ionization energy. So first is down the group. Okay. Let's see what happens to the ionization energy when we move down the group from top to bottom. So it is decreasing. Okay. Now why is it decreasing? Let's understand this thing. So it is decreasing because the factors on which it is depending, the atomic size and the nuclear charge. Okay. What is happening to them? Let's try to understand. So when we are moving down the group, we all know atomic size increases and nuclear charge also increases. Okay, because the atomic number is increasing. But the same story, the increase in the atomic size is more than the increase in the nuclear charge. Okay, so the effect of increase in the atomic size, okay, or the effect due to increase in the atomic size would be more than the effect due to the increase in the nuclear charge. Now, what is the effect due to the increase in the atomic size on ionization energy? Simply try to just remember in this way, atomic size is increasing, electron is moving farther and farther away from the nucleus. So, nuclear pull would be lesser and lesser on that electron. Nuclear pull is lesser and lesser. Energy required to remove that electron would be lesser and lesser. So, ionization energy would be decreasing, right? And in case of nuclear charge is increasing, we all right now saw that when nuclear charge is increasing, the electron is pulled more strongly, right? So, more and more energy would be required to remove the electron. Means ionization energy which is required is also more and more. So, what is happening? Ionization energy is also increasing. Okay. Now, what I said, the effect due to the increase in the atomic size would be more. So, the decrease would be more than the increase. Okay. Decrease in the ionization energy would be more than the increase in the ionization energy. So, see what would be the net effect? Net effect would be decrease, and that's why ionization energy is decreasing. Okay, very simple. Now, let's see an example. See, these are the group 1 elements. We all know what is happening to the ionization energy. Okay, when they are measured, the ionization energy are measured in kilojoules per mole, and you can clearly see lithium, sodium, potassium, rubidium, cesium. They are having respectively the ionization energies as C 520, 496, 419, 403, 374. We can clearly conclude that ionization energy is decreasing, okay, from this example as well. Okay, now let's see the variation of ionization energy or trend of ionization energy when we move across the period from left to right. Okay, now this left to right is very important. Okay, now what happens to the ionization energy? It is increasing, but with exceptions. Okay, now let's see the exceptions later on. First, try to understand why is it actually increasing. Okay, so the answer, the same type of answer, since ionization energy is depending on two factors, atomic size and nuclear charge, and since atomic size and nuclear charge, okay, when we move across the period from left to right, we know atomic size decreases, and since atomic number increases, we know nuclear charge increases. Okay, now since atomic size decreases, we have just now studied, okay, the factors on which ionization energy depend. First, atomic size. So when atomic size was increasing, ionization energy was decreasing. Okay, but now atomic size is decreasing. Okay, so ulta, opposite, ionization energy would increase. Simple. And nuclear charge increases, we know ionization energy increases. So what is the net effect? Net effect is increase, right? Therefore, ionization energy increases when we move across the period from left to right. Very clear. Now, let's see the examples, and while seeing the examples, we would also see the exceptions as well. Okay. So second period elements: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Now you can observe the ionization energies. So here lithium is having 520, beryllium is having 899. Okay, fine. The ionization energy is increasing. Yes, it should. But later on, see, in case of boron, it's 801. Oh, so this means that beryllium is having more ionization energy than boron. Okay, now this is not fitting in our trend, right? Beryllium should have less ionization energy than boron, but it is showing more ionization energy than boron. That's why, see, this is an exception. Okay. Now again moving ahead, from boron to carbon, it is increasing. From carbon to nitrogen, it is increasing again. But from nitrogen to oxygen, it is decreasing. So in this case as well, nitrogen should have Okay, ideally it should have less ionization energy than oxygen, but it is having more. That's why it is also an exception. Okay, now then again moving ahead from oxygen to fluorine and from fluorine to neon, it's all set. Okay, the ionization energy is increasing very regularly. Same pattern you would observe when we would see the third period elements. From sodium to magnesium, magnesium would show exceptional behavior because it is having more ionization energy than aluminium. Similarly, phosphorus would show the exceptional behavior because it is showing more ionization energy than sulfur. Okay, rest all elements would be showing a gradual increase in the ionization energy. Now, very much important one more thing. See, this group 1 elements, okay, you can observe throughout the period the least ionization energy is possessed by this group 1 elements, 520 in this case, and in this case sodium is having 496, and throughout the period this group 18 elements are having the highest ionization energies, 2080, 1520. Okay, you can just compare. 2080 is highest among the group period number 2 elements, and 1520 is highest among the period number 3 elements. Okay, so this thing you have to remember. Group 1 elements have least ionization energies in a period, and group 18 has highest ionization energies in a period. Okay, now one more interesting thing, the metals are having very low ionization energies, okay, whereas non-metals are having high ionization energies. Okay, why is this so? Let's try to understand this thing logically. See, we all know that metals have tendency to lose electrons, right? Now if they have tendency to lose electrons, which means they are readily willing to give up the electrons, so very less amount of energy would also do the work. Very less amount of energy if we apply, the electron can be easily removed because metals are willing to give the electrons. So very less amount of energy means less ionization energy is required. That's why we say that, okay, less ionization energy is required. That's why we say that metals are having low ionization energy. Okay, now in case of non-metals, the case is totally opposite. They are like hungry for electrons. They have the tendency to gain electrons. So do you think they would readily give up electrons, or it would be easy to take the electrons from them? The thing for which they are hungry, we are trying to take that very same thing, and it's very dangerous to do. Okay, I'm just joking, but it is very difficult to remove the electron from non-metals, okay, because they have strong tendency to gain the electrons. They won't give up electrons readily. So in order to remove the electrons from the non-metals, since it is difficult, we need to apply a huge lot amount of energy, and the high energy which we have to apply, okay, indicates that non-metals, okay, we have to apply high energy. So non-metals are having high ionization energy, because energy which is required to remove the electron is ionization energy, and we are applying high energy to remove the electron. Therefore non-metals would have high ionization energies. Okay, very simple. Now with the existing knowledge about the ionization energy, or the concept of the ionization energy which we have learned so far, let's try to find out the element which is having highest ionization energy in the periodic table and the element which is having lowest ionization energy in the periodic table. Okay, so I'm going to first find out the element having highest ionization energy. So you can pause the video right now, try to find out on your own, try to apply your brains. Come on, okay. Chalo. Now in the entire periodic table, what we have learned so far, okay, about ionization energy, we have learned the trends, okay, and these trends would help us to find out the highest ionization energy, or element having highest ionization energy, or the element having lowest ionization energy. Now how is it possible? See, when we learned that when we move across the period okay, what happens to the ionization energy? Ionization energy, it starts to increase, okay, and we also learned group 18 has the highest ionization energies and group 1 has the lowest ionization energies. Okay, so the hint for the next answer. Now let's focus on this one first. So group 18 are having highest ionization energies, so this means that our answer is from group 18. Very clear. Now among the group 18 elements, who has the highest? Once we find that element, we got our answer. So among group 18, how we would find who has the highest? Try to remember the trend of ionization energy when we move down the group. What happens to the ionization energy? Down the group, it decreases. Very simple. So when we move down the group, if it is decreasing, okay, this means that radon would have the least ionization energy among the noble gases and helium would have highest ionization energy, right? So we got our answer. Helium has the highest ionization energy among all the elements in the periodic table. Okay, what's the value? No need to remember it. 2372 kilojoules per mole. Okay, now I have also given you the hint to find out the lowest ionization energy, the element having lowest ionization energy. Okay, you can pause it right here and then try to find out. So among these, all these elements are having lowest ionization energies, but among these, which one is having the least? Okay, that would be our answer. So again, remembering the trend down the group would give us the answer. So down the group, what happens? Ionization energy, it goes on decreasing. Okay, so when we would move from lithium to sodium, potassium, rubidium, cesium, let's not take the case of francium, it's radioactive. Okay, so let's remove that, means let's not talk about this element. Okay, we would just end up till cesium, and this cesium would be having the lowest ionization energy because ionization energy is decreasing down the group. Okay, so our answer would be yes, cesium. It is having 375 kilojoules per mole. Okay, this is the value. No need to remember it. That's it. Okay, now next topic is electron affinity. So let's try to understand what actually electron affinity means to us. Okay, very simple. Okay, in simple terms, its name only suggests us that affinity, affection for electron. Okay, that's it. But in terms of energy, let's try to understand what does it mean. So we are going to see a story. At the end of the story, you would definitely remember what actually electron affinity is, and also you would remember its definition as well. Okay, so I have taken an atom here. We know the atoms are neutral, and also what I have did is I have isolated this atom from all other atoms. Okay, so this is also an isolated atom, and then I have converted whatever state it is in, I have converted it into the gaseous state. So it becomes a neutral isolated gaseous atom. Okay, now what I'm going to do is I want that this atom should accept an electron. So I'm going to make this atom to accept the electron. But what happens then? After accepting this electron, it would become negatively charged because it would have one electron more. Okay, so it would become negatively charged gaseous ion. Because why gaseous? It is in still gaseous state. The atom is in gaseous state, that's why the ion would be in gaseous state. So negatively charged gaseous ion. And after accepting this electron, oh boom, magic, it would release the energy. Okay, and this very energy is called as electron affinity. Okay, very simple. So electron affinity is the energy released, we can see in this equation, while converting a neutral isolated gaseous atom into a negatively charged gaseous ion. See here, negatively charged gaseous ion by the addition of electron. Okay, now it is also called as electron gain enthalpy, and it is simply measured in the units electron volt per atom, and the SI unit to measure electron affinity is same as that of the ionization energy, kilojoules per mole. So the electron affinity values are represented by a negative sign. Okay, so let's try to understand this with the help of an example. So this is a chlorine atom, neutral isolated gaseous atom. I am making it to accept an electron, then it gets converted into a Cl minus ion. This is a negatively charged gaseous ion, okay, of chlorine, and with this it also releases energy which is called as electron affinity, right? And suppose this energy is x kilojoules per mole. So what is the use of this negative sign? Right now I'm going to tell you. We can write that from this equation the chlorine has electron affinity, okay, which is minus x kilojoules per mole. Okay, so whatever energy in kilojoules per mole is released, we would just represent it in the form of minus energy kilojoules per mole. Okay, so this is how we use the negative sign. Now, very much important concept. Okay, you have to remember this because we are going to use this. Okay, which is more negative is the electron affinity value. Okay, more negative. Just try to remember the number line. When the value is going to be more and more negative, okay, which is here. Okay, what that value suggests us that the particular element is readily gaining the electron. Okay, it is easier to gain the electron for that element. Very clear? Okay, now let's see the factors on which electron affinity depends. Simply, it depends on atomic size and nuclear charge, we all know, and we are going to see how the electron affinity varies when atomic size increases and nuclear charge increases. But before that, let me give one disclaimer to you that we are going to understand this concept based on the simple explanation for the electron affinity, which simply means that simple explanation for the electron affinity, okay, which I have already explained you that electron affinity simply means affinity for the electron. Okay, that's it. Affection for the electron, attraction for the electron, that's it. So what I'm going to do is I have taken an atom. Okay, this is the outermost electron, outermost shell, and this electron, outermost electron, is experiencing some nuclear pull. Okay, now what I'm going to do is I'm going to increase the size of the atom. Okay, so what is happening after increasing the size? This is the outermost shell, this is the outermost electron, and this outermost electron is experiencing some nuclear pull, right? Now when I'm saying I'm increasing the size of the atom, it's like hypothetical. Okay, I cannot increase the size of an atom. I want to tell you that I am taking another atom having a larger size, simply. Okay, now this is the another atom having a larger size. So we can clearly make out that the nuclear pull experienced by this electron, okay, is more as compared to this electron. Very clear? Now can I say that the affinity for this electron, okay, from the nucleus is more as compared to this electron. Okay, since the attraction here is more, attraction here is less from the nucleus. So what is happening? See, when I'm increasing the size, okay, the attraction for the electron is decreasing. Okay, or we can say that the affinity for the electron is decreasing. That's it. So when we increase the size, electron affinity decreases. Now let's see what happens to the electron affinity when nuclear charge increases. The same story we are going to repeat. Okay, outermost electron, outermost shell, and this is the nucleus. This electron is experiencing some nuclear pull, but when we are increasing the nuclear charge, we all know that the pull experienced by this electron, okay, nuclear pull experienced by this electron would be more. Okay, so can I say that after the increase of the nuclear charge, okay, this electron is experiencing more affinity, right, from the nucleus. So if it is experiencing more affinity when the nuclear charge is increasing, okay, so I can say that electron affinity is also increasing, simply. Okay, now let's see the trends shown by the electron affinity. First is down the group. When we move from top to bottom, what is happening? Electron affinity is decreasing. Okay, so why is this so? Very simple, because when we move down the group, we know that atomic size increases and nuclear charge also increases. Okay, but the scenario is, the twist in the story is, we already know that the increase in the atomic size, okay, is much more than the increase in the nuclear charge. Okay, so what is happening then? Because of this, the effect, okay, due to the increase in the atomic size would be more than the effect due to increase in the nuclear charge. Okay, so the net effect would be due to the increase in the atomic size. Very clear? Okay, due to the increase in the atomic size on electron affinity decreases. Okay, right now we have seen. So as I already said you that the net effect would be due to the increase in the atomic size, right? Now due to the increase in the atomic size, electron affinity decreases. That's why we observe decrease in the electron affinity when we move down the group. Okay, so in this way it is like an elongated explanation, but for 1 marker questions you can just simply write down that electron affinity decreases because since when we move down the group, atomic size as well as nuclear charge increases, but the effect of increase in the atomic size is more than the effect of increase in the nuclear charge. That's why the net effect would be due to the increase in the atomic size, which is decrease in the electron affinity. That's why electron affinity decreases when we move down the group. Very simple. So now let's see the example. Group 1 elements. Now you can clearly see the electron affinity values in kilojoules per mole. They are appearing to be decreasing when we move down the group. See, minus 60, minus 53, minus 48, minus 47 for lithium, sodium, potassium and rubidium respectively. Okay. So one more conclusion we can make from these values is that, can you clearly observe that the values are becoming less and less negative? Okay, less and less negative means, see, this is the number line we all know. Now from minus 60 to minus 50 to minus 47, they are approaching the positive values. So we are just saying that they are becoming less and less negative. Okay, if they are approaching more and more, if they are approaching negative values, or if they are increasing in the order, okay, where they are approaching negative values, we can say that they are becoming more and more negative. So that's why we are saying that's why we are just saying that they are becoming less and less negative. Okay, so we can conclude from this value that yes, electron affinity values, when we move down the group, they not only decrease, okay, but they also become less negative. Now let's see the trend of electron affinity when we move across the period from left to right. Okay, so what is happening? Electron affinity is increasing. Okay, now why is this so? Very similar type of logic we are going to use, we all know, because when we are moving from left to right, atomic size is decreasing, right? But nuclear charge is increasing. Okay, now what's happening? Both of these factors are contributing to the increase in the electron affinity. Okay, we have already studied decrease in the atomic size, okay, would result into increase in the electron affinity, because what we studied, the case was when atomic size increases, electron affinity is decreasing. So this is totally opposite case. When atomic size is decreasing, then electron affinity would be increasing. Okay, now nuclear charge, when it is increasing, we already studied that electron affinity increases. Okay, so both of these factors have net effect, which is increase in the electron affinity. That's why electron affinity increases when we move across the period from left to right. Okay, so now you can see here the example of group 2, group 3, period number 3, period number 3, period number 2 elements, okay, as well as the period number 1 elements. Okay, but we are going to focus more on period number 2 and period number 3 elements. Okay, so you can clearly here see from minus 60 to minus 88, minus 122, minus 141 to minus 328, values are increasing. Okay, electron affinity values are increasing. Here also minus 53, okay, just leave here minus 50, minus 19, minus 74, minus 200, minus 349. Okay, the net, you just focus on the net increase. So see, from minus 53 it is moving to minus 200 and to minus 349. So what is happening? The values are increasing. Okay, don't worry, I'm going to explain you why there is a deviation in the values, but for now the general trend which is shown by the electron affinity is the values are increasing when we move across the period from left to right. Or we can also see from minus 60 to minus 328, the value is becoming more and more negative. Okay, so we can also say that electron affinity becomes more negative as we move from left to right in a period. Now very interesting thing, see this group 1 elements, minus 73, minus 60, minus 53, you can observe this minus 60 value among this entire period, it's the least, right, of electron affinity. Here minus 53, it's the least. Okay, except this. So what this data or what this information is actually helping us to understand, that the group 1 elements are having the least electron affinity values. Okay, while in the same way you can see here group 17 elements, minus 328, minus 349, you can see minus 328 is the highest among the second period. Okay, as well as minus 349 is also highest among the third period. So we can clearly infer from here that these group 17 elements, okay, have highest electron affinity values. Okay, so just now when we studied the variation of electron affinity across the period, okay, when we were observing the values in this table, we observed that the values are, means the trend is not perfectly followed. Okay, if the electron affinity value is increasing, it is not perfectly followed. Now why is this so? Because there are few exceptions. Okay, now let's see one by one what are the exceptions. So first, very simple exception is group 2 and group 15. Okay, so these two groups, they don't show, okay, regular trends in their electron affinity values. Okay, now moving to the next exception. So if you could make out from the table, you would quickly observe that, or you could like make out that fluorine, chlorine, okay, they both have the electron affinity values, but there is some mismatch in them, because we just now studied that when we move down the group, electron affinity decreases, right? Electron affinity values go on decreasing, or they become more and less negative, right? But here you can see here the value is increasing from 328 to 349, value is increasing, or we can just likewise also say that the value is becoming more negative. Okay, instead of becoming less negative, it is becoming more negative. And same case you can observe in case of oxygen and sulfur, the value actually should be decreasing, but from 141 to 200 it is increasing. And also see, from minus 141 to minus 200 it is becoming more negative. Okay, so it should actually become less and less negative. Just now we studied, right? So now why is this happening? Why these values, why these pair of elements, oxygen and sulfur, fluorine and chlorine, show exceptional electron affinity values? The reason is very simple. See, these oxygen and fluorine atoms, okay, they are having the sizes, okay, very small. So due to their exceptionally small sizes, what is happening? The sulfur and chlorine are having, they don't have such small sizes, okay. And we also know that when we move down the group, atomic size increases, okay. So they are having comparatively larger sizes than oxygen and fluorine, and their sizes is not their sizes are not exceptionally small like that of oxygen and fluorine. Okay, so what is happening when we are trying to make the oxygen and fluorine gain an electron, okay, or when an electron is gained by oxygen or fluorine, okay, there seems to be some electron repulsion, okay, because of their small size. Already because of the small size, the electrons are present in the outermost shell, okay, and because of their small size, when a new electron is getting added, so it is feeling repulsion from other electrons, okay. Also the size is small, right? So you only imagine, if you have been given a small room to accommodate, there are already 6 electrons and 6 people in that room, and you are pushing that 7 person in that room, there would be some kind of repulsion between them. Means the 6 people won't like that, oh, 7th one, why is he coming now? Actually there is already very less space, and why one more guy is coming? Okay, so the same thing is happening with oxygen and fluorine. They are not very happy with the addition of an electron, so they show an electron repulsion. Okay, same case happens with fluorine as well. It also shows electron repulsion when the electron is being added. Okay, now in case of sulfur and chlorine, the electron repulsions are present, but they are not that much. Okay, the size of the room is bigger than that of the oxygen for sulfur, and for chlorine as well the size of the room is bigger than that of the fluorine. Okay, so less electron repulsions are taking place. Now what actually I want to tell you, see, we have learned a concept that more negative is the electron affinity value, okay, easier it is to gain electron, right? And I have told you to remember this concept because we are going to use it. So now you can clearly make out which one of the following, okay, out of oxygen and sulfur, which one of them could easily gain the electron. Okay, either oxygen or sulfur. So you're right, yes, sulfur, yes. So why? Because the electron repulsions here would be less because of the larger size, so it would easily gain the electron, right, than the oxygen. So this means that it would have more negative electron affinity value. Okay, that's the reason it is having more negative electron affinity value than oxygen. And the same case is observed in case of fluorine and chlorine. Since it is easier to gain the electron in chlorine than fluorine, okay, so the chlorine is showing more negative value than the fluorine. Now moving to the third exception in the table, if you would have observed very clearly, the value for electron affinity for helium, okay, of helium is positive. Now this is something new to you, because till this point we have learned that the electron affinity value is represented by a negative sign. Now why is this helium showing a positive electron affinity values? And likewise neon and argon as well show positive electron affinity values. Now why is this happening? Okay, this is an exception. So what we studied, that when we see the trend of electron affinity, okay, across the period, the values become more and more negative, but suddenly the value becomes positive. Okay, here neon shows positive value after fluorine. So this is an exceptional behavior. Now why is this happening? Let's see. Okay, so we all know that these helium, neon, argon, krypton, xenon, radon, these inert gases have stable electronic configuration. Okay, very stable. They are having their outermost shell completely filled. Now you only imagine, okay, a saint which is sitting on any mountains in the Himalayas or anywhere, okay, any mountains, a very quiet place. He is meditating very calmly and in very focused mode. Now, do you think that the saint would be happy if someone would just come and push him or just disturb him? Absolutely not. Same is the case with these inert gases. They are very stable, okay, very stable. So they don't want any other thing to disturb them. Okay, so they don't have actually the tendency to either gain electron or to lose electron. We already know. Now since they're not happy to gain electron, now when we are trying to make them gain electron, they are strongly resisting. Okay, so now what we have studied the concept, again I'm going to write it down. Okay, more negative is the electron affinity value, it means that easier it is to gain the electron. Okay, now in this case it is very difficult to gain the electron. Okay, and it is, suppose it is difficult. Okay, so what would be the electron affinity value? What would happen to the electron affinity value? Electron affinity value would become less negative. Okay, so from more negative values, okay, the electron affinity value would become less negative if it is difficult to gain the electron. But now in this case, it is very much difficult to gain the electron. So electron affinity values are just crossing that zero barrier and entering the positive values. And this is the reason why the inert gases are having positive electron affinity values. So moving to our last periodic property, electronegativity. So in the same way, we are going to understand what actually electronegativity is with the help of a simple story. So pay attention now. After the end of the story, at the end of the story, you would definitely get what actually electronegativity means to us. Okay, so this is an atom, this is another atom. Both of these atoms are like they are feeling to combine. Okay, so but when they are combining in some different way. So this atom has electrons in its outermost shell. This atom also has some electron in its outermost shell. But while they are combining, they are like sharing their electrons, okay, with each other, which sharing their electrons of their outermost shell with each other. Okay, so now suppose they are combining by sharing one electron. Okay, one electron from this atom and one electron from this atom. Okay, now what we call this as, if there are two electrons, we call it as a pair, and since these are shared, so we call them as shared pair of electrons. Okay, shared pair of electrons. Now what is happening, the atoms, okay, which are sharing this electron, both of these atoms now try to attract this electron towards themselves. And this very tendency of the atom, okay, in a molecule to attract the shared pair of electron towards itself is called as electronegativity. Okay, so that's the actual definition as well. Very simple. We have learned it with the help of story. So see, the tendency of an atom, okay, suppose this atom, in a molecule to attract shared pair of electrons, see, to attract shared pair of electrons towards itself is called as electronegativity. Okay, now since it's just a tendency, so it doesn't have any unit, so it is dimensionless property. Okay, but scientists have tried to give various scales in order to measure electronegativity. Now out of that, the most widely used is the Pauling scale. Okay, and in this Pauling scale, if you observe, the electronegativity value, okay, the highest electronegativity value in the Pauling scale is given as 4 and it is given to fluorine, and the lowest electronegativity value, okay, in the Pauling scale is 0.7 and it is given to cesium. Okay, now let's see the factors on which electronegativity depends. We all know atomic size and nuclear charge, it would depend on atomic size and nuclear charge. And now first we are going to see what happens to the electronegativity when atomic size increases. So I am taking an example. Now this is a slightly different type of example. So here this is the atom, okay, which I am considering. It is combining with some other atom, okay, and while combining it is sharing its electron, and this atom is also sharing its electron. So suppose one electron is being shared, so this is the shared pair of electron, okay. Now this is the nucleus of the atom, so this nucleus is pulling these electrons, okay, with some attractive force. Now consider another case in which I am taking an atom which is having a slightly more size, okay, than this atom. Now this is also combining with some other atom. These are the shared pair of electrons. Its nucleus is also pulling the shared pair of electrons with some attractive force, okay. Till now the story is very simple and clear, but what you can observe here now, see, since the shared pair of electrons are closer to this nucleus, they would be attracted, okay, the shared pair of electrons would be attracted more strongly by the nucleus in this case than this case, okay. Here they are farther, okay, so the shared pair of electrons would be attracted, but the attraction for the shared pair of electrons would be less in this case than this case, okay, vice versa, in whichever way we want to understand, okay. So I'm taking this one, the shared pair of electrons are being attracted by the nucleus more strongly than this case, okay. Now what is happening then? If they are being attracted more strongly, then the tendency to attract the electron is more here as compared to that case. So if the tendency to attract the electrons is more, what does it mean? Yes, tendency to attract the shared pair of electron is electronegativity. So electronegativity here is more. I am showing it by two sticks, okay, yeah, two lines to show it more, okay. So electronegativity here is more as compared to the electronegativity here, okay. Why? Because the tendency to attract the shared pair of electron here is more than this case. So what is happening? See, when we are increasing the size, electronegativity is decreasing, okay. Now let's see what happens to the electronegativity when nuclear charge increases, okay. So again the same type of examples. This is an atom combining with another atom by sharing this two electrons, okay, by sharing these, both are sharing these two electrons. So this is the shared pair of electron and this is the nucleus of this atom, so it is attracting the shared pair of electron with some attractive force. Now I'm again taking another atom which is combining with some other atom, okay. These are the shared pair of electrons, okay, this is the shared pair of electrons, and here the nucleus, okay, in this case here the nuclear charge is more, okay, than this case. So now you can clearly conclude that if the nuclear charge here is more, it would strongly pull the shared pair of electrons towards itself, right, as compared to this case, okay. Now if it is strongly pulling the shared pair of electrons towards itself, it is having more tendency to attract the electron, correct, as compared to this case. Now if it is having more tendency to attract the electron, this means that the electronegativity here, okay, would be more than the electronegativity here in this case, okay. So I'm showing more with these two sticks and one stick is for less, okay. So what is happening? When the nuclear charge is increasing, electronegativity is also increasing, okay. Now let's see the trends shown by the electronegativity. First, when we move down the group from top to bottom, okay. So what is happening to the electronegativity? Electronegativity is decreasing, okay. And why is this so? Very similar reason, okay, very same type of reason to all that of all the periodic properties, okay. The logic is absolutely same. What is happening? When we are moving down the group, atomic size is increasing and nuclear charge is also increasing, okay. So we already know the twist in the story, that increase in the atomic size is more than the increase in the nuclear charge. So the effect due to the increase in the atomic size would be more than the effect due to the increase in the nuclear charge. So what would be the net effect then? Net effect would be due to the increase in the atomic size, correct. And now what is the effect due to the increase in the atomic size on electronegativity? Very simple, just now we studied electronegativity would decrease, okay. So that's why electronegativity decreases when we move down the group. Very simple. Now let's see an example. See, the most electronegative elements are fluorine, chlorine, bromine, iodine, astatine, okay. We will see it in the next part when we are going to see the variation of the electronegativity across the period. But still, this group fluorine, chlorine, bromine, iodine, astatine. Okay, see their electronegativity values. Just now what I said when we studied electronegativity, what actually means electronegativity is, okay, when we studied that, I told you in the Pauling scale fluorine has 4.0, means 4 value. Okay, so here see, fluorine is having value is 4. Okay, then chlorine 3, bromine 2.8, iodine 2.5, astatine 2.2. So you can clearly see here that the value of electronegativity is decreasing as we move down the group. Now let's see what happens to the electronegativity values, okay, or the trend of electronegativity when we move across the period from left to right. So electronegativity is increasing. Now why is this so? Very simple, because when we move from left to right, atomic size decreases, right, and nuclear charge goes on increasing because atomic number is increasing, right? But now both of them, what effect they are showing? Due to the decrease in the atomic size, okay, the electronegativity increases. We already have learned this. Okay, we have learned the vice versa case. Okay, with the increase in the atomic size, electronegativity is decreasing. We have learned this part. Okay, when we were learning the factors on which electronegativity depends. Now here now in this case, see here the thing is totally opposite. Atomic size is decreasing. Okay, so if the atomic size is decreasing, electronegativity would be increasing. Okay, opposite to that of. So here electronegativity is increasing, we know. Now with the increase in the nuclear charge, we also know that electronegativity increases, right? We have already studied this. Now both of these factors are what they are showing, increase in the electronegativity. That's why when we move across the period from left to right, electronegativity increases. Now you can see the values of electronegativity here. See, second period, third period and fourth period elements I have taken. So you can gradually observe from 1, 1.52, 2.53, 3.54, values are increasing. Here in this case 0.9, 1.2, 1.5, 1.8, 2.1, 2.53, okay, values are increasing. Similarly in the fourth period as well, the values are appearing to be increasing. Okay, now interesting thing is, if you have a closer look in this table, lithium, sodium and potassium, okay, they are having the least electronegativity values in their periods. So you can see one electronegativity value in this entire period is only possessed by lithium. Okay, so the least value is possessed by lithium. Below 1 there is no electronegativity value here present. Okay, similarly below 0.9, no other element in this period is showing the value below 0.9. Okay, and similarly here below 0.8, no other element is showing the values of electronegativity, okay, in fourth period. So these elements, okay, the group 1 elements are having the lowest or least electronegativity values in their periods. And similarly you can clearly see the group 17 elements, okay, fluorine, chlorine, bromine, as you can observe 4 in this entire period, the 4 is the highest value which is possessed by fluorine. Similarly chlorine and bromine's case also 3 and 2.8 are the highest value in their respective periods. So these group 17 elements have highest electronegativity values in a periodic table. Now we have just now seen that from the data, okay, the group 1 elements were having lowest electronegativity values, while the group 17 elements were having highest electronegativity values, and the electronegativity values were like increasing across the period very gradually. So we can clearly make out that since here see the group 1 are having the lowest electronegativity values, okay, so lowest electronegativity values, okay, these are having the least electronegativity values, but the lowest would belong to this side of the periodic table. Okay, and since the group 17 are having the highest electronegativity values, the high electronegativity values would belong to this part of the periodic table. Okay, so and now we already know that this part of the periodic table has metals, so they are having low electronegativity values then. Okay, we just now saw, and this part we have just now saw that they are having high electronegativity values, and this part are mostly having non-metals, so therefore non-metals are having high electronegativity values. Okay, now since they are having low electronegativity values, okay, since metals are having low electronegativity values, we can call them as electropositive, right, the opposite of electronegative. So that's why we call metals as electropositive, okay, elements, and we call non-metals, since they are highly electronegative, we call them as electronegative elements. Okay, now one more interesting thing, this period number 2 elements, okay, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, these elements show exceptional behavior from the other elements of the respective groups. Okay, which means that to state in a simpler terms, lithium shows different behavior than sodium, potassium, rubidium, cesium. Okay, beryllium shows different behavior than magnesium, calcium, strontium, barium. Now, why is this so? Very interesting. See, this period number 2 elements are having very small size. They are having exceptionally small sizes and high electronegativities, and this is the reason they are behaving in a different way. Now let's see a very important question, that why noble gases do not show electronegativity. Okay, till now we haven't discussed about the electronegativity of noble gases, right? Now why is this so? Because they actually do not have electronegativity. And why they don't have electronegativity? Why they don't have the tendency to attract the shared pair of electrons? Because the reason is very simple. They exist in monoatomic state. Okay, now what does this mean? Suppose I'm taking an atom of helium. So this helium atom exists as helium atom. It won't even combine with another helium atom. Okay, leave the point that it would combine with the atom of some other element. It won't even combine with the helium atom itself. Okay, so since it is existing in monoatomic state, now it's very logical to think that how there would be shared pair of electrons. There is no question of the shared pair of electrons here in this case. So the attraction is then again a far away concept. Okay, so there is no question of even attraction of shared pair of electrons, because the shared pair of electrons don't exist here. Okay, now why they are existing in monoatomic state? This is also interesting to know. Very simple, we already know that these are having stable electronic configurations, right? They have the complete octet, so they don't feel to either lose electron, gain electron, and in this case they don't feel even to share electrons, right? So no sharing of electrons, no shared pair of electrons, so no question of attracting the shared pair of electrons. That's why they don't have electronegativity. Now moving ahead to the next topic, diagonal relationship. What does it mean? So we found that the properties of the elements in the second period, okay, suppose here lithium, beryllium and boron, okay, these are the second period elements, their properties are found to be similar, okay, resemble with the elements in the third period. Okay, these are the elements in the third period of next group, which are at the right diagonal to the second period element. Okay, now let's understand this thing. See, the properties of the elements in the second period, okay, are found to be similar with the elements are found to be similar with the properties of the elements, okay, of third period. This is the third period of next group. So this means in case of lithium, the element is from the next group and third period. In case of beryllium, the element is from next group to that of the beryllium and third period. In case of boron, the element is from the next group and third period. And also these element we have just now seen that it is at the right diagonal of the second period element, and it is also at the right diagonal of the second period element, right diagonal of the second period element, right diagonal of the second period element, and this relationship, okay, is called as diagonal relationship. So see here, we can clearly make out lithium's to its right diagonal, magnesium is present. Okay, beryllium's position, this is beryllium's position, to its right diagonal, aluminium is present. Okay, boron's, this is the boron's position, to its right diagonal, silicon is present. Okay, and these elements are also from the next group and third period. Okay, now this relationship we just now saw, it is called as diagonal relationship, and this elements, okay, lithium, magnesium, beryllium, aluminium, boron, silicon, are found to be similar with the properties of the third period element of next group, which is at the right diagonal to that the second period element. Very simple. Now, what is the cause of this diagonal relationship? What actually is making the properties of the elements similar? Okay, very simple. The properties, okay, of the elements are generally found to be decreasing across the period, okay, and increasing when we are moving down the group. Okay, now let's understand this thing with the help of an example. Atomic size. Now here in the case of lithium, the atomic size is 152 picometer, while in case of magnesium atomic size is 160 picometer. Okay, now let's understand why their atomic sizes are quite similar to each other. Okay, 152 and 160 are quite close. So why is this so? The reason here they have given. Okay, the atomic size trend is generally it is found that the properties are having increasing trend down the group and decreasing trend across the period, and same is shown by atomic size. It is also increasing as we move down the group and decreasing as we move across the period. So here see, you can clearly make out from lithium to beryllium it would decrease, so the atomic size of beryllium would be less than 152 picometers. But again when we would move from beryllium to magnesium, it would again increase, and that's why its atomic size reaches 160 picometers. Okay, and then we just found out that yes, oh, they are having similar atomic sizes. Now let's see an interesting fact about a stable elements and radioactive elements. Okay, so stable elements have neutron to proton ratio, okay, around 1. Okay, now for example we can see sodium, potassium, calcium, and to cross check as well, let's try to see the neutron to proton ratio of sodium. Okay, so sodium is having atomic mass 23, atomic number 11. Okay, and we can calculate the number of neutrons from the atomic mass and atomic number, right? We know atomic mass minus atomic number, because this is the total number of protons plus neutrons. Okay, it's 23, and we know the number of protons from the atomic number, it is 11. Okay, so atomic mass A is this, atomic number is 11. Okay, Z, and we already know the formula that A minus Z would give us N, right, number of neutrons. So 23 minus 11 would give us 12, right? So number of neutrons is 12, and here the neutron to proton ratio would be 12 upon number of protons is 11, so it would be roughly around 1, right? So this special characteristic is shown by stable elements. Their neutron to proton ratio is around 1. You have to remember in this way. Okay, you can remember with the help of an example as well. Now what is the fact about the radioactive elements? Okay, these have neutron to proton ratio 1.5 and above. Okay, so it can be 1.5 or above 1.5. So let's take an example of francium. Okay, so francium has atomic weight 223 and atomic number 87. Okay, no need to remember these things, I'm just trying to demonstrate you. So when we would minus 223 from 87, what would be it? It would be like 136. Okay, so number of neutrons is 136, protons is 87. Now if you would calculate, okay, you can use the calculator as well, or if you would calculate, you would approximately get the answer as roughly around 1.5. So we also had checked a cross check, we also did for the radioactive elements, that do they have neutron to proton ratio 1.5 and above. Okay, now let's quickly solve some few questions. Okay, so to check whether how much you have understood. So what I have already suggested you can pause the video here itself, you can read the question and try to attempt on your own. Okay, after that you can again resume it and then check your answer. Okay, so moving to the first question, the most electronegative element from the following element is magnesium, chlorine, aluminum, silicon. Which is the most electronegative element from them? So what we would do, I already told you in the previous video as well, when we are having some elements, let's try to locate them first. So try to see whether they first belong to the same group or same period. So see, magnesium, chlorine, aluminum, silicon, I think they are belonging. Yes, you would be it would have been clicked in your mind that yes, this belong to the third period, right? Sodium, magnesium, aluminum, then silicon, phosphorus, sulfur, chlorine. Okay, so these are third period elements. So let's try to arrange them. Okay, magnesium, sodium, magnesium, then after magnesium comes aluminum, then silicon, phosphorus, and our element is sulfur, and after sulfur there is chlorine. Now which is the most electronegative element? Very easy to find out. We know the trend of electronegativity, we have to just apply it. Now since these belong to the same period, we would apply the trend of period. Okay, so what happens to the electronegativity when we move from left to right in a period? Electronegativity increases. Yes. Okay, so this means that most electronegative element would be chlorine, because it would increase, and this would have the highest electronegativity. So therefore our answer is chlorine. Okay, now This was asked in your examinations in 2019 as well. Okay, so quite interesting. Let's see the next question. Name the periodic property which relates to the character of element which loses one or more electrons when supplied with energy. Okay, so now what we have to just pay attention to in this question, it's very simple. We have to just pay attention to the character of the element which is losing one or more electrons. That's it. Okay, so if an element is losing electron, what does this mean to us? This element is behaving like either metal or non-metal. We have to just figure out. So we know metals have tendency to lose electrons. So this is behaving like metals, right? And if it is behaving like metals, we know that this element is showing metallic character, like, right? Metallic character. We know what does it mean? Metal-like character. Okay. So since it is behaving like metals, therefore it is showing metal-like character or metallic character. So our answer is metallic character. Next is question number 3. This question refers to the elements of the periodic table with atomic numbers from 3 to 18. Okay. Some of the elements are shown by letters. Okay. But the letters are not the usual symbols of the elements. Okay. So don't get confused with them. Okay. Now, which of these A have least ionization energy? So they are asking us among all these elements which are having least ionization energy. So we have already studied right now that ionization energy. Now we can compare it in the, now we can see there are two periods. So let's try to solve this question by remembering the trend for ionization energy across the period. What is happening to the ionization energy when we move across the period? Ionization energy increases. Okay, we have already studied this thing. So if the ionization energy is increasing, okay, how you would quickly relate and correlate to this thing? Okay, we know that across the period atomic size increases, across the period nuclear charge increases. So what you can think in your brain that atomic size is across the period atomic size is decreasing. Okay, sorry, and across the period nuclear charge is increasing. So we can correlate in your brain that atomic size is decreasing, so electron is moving closer to the nucleus, so difficult would be to remove that electron, so more energy is required, ionization energy is increasing, as well as nuclear charge is also increasing. So nuclear charge increases means electron is being pulled more and more strongly, more and more energy is required, so more and more ionization energy is required. So both the factors are suggesting us that ionization energy is increasing. Okay, no need to remember. Okay, just quickly apply the logic in your brain, which we have studied. The reason you should quickly remember, that's it. You could remember the answer as well, what is happening across the period and down the group. And at the end of the chapter, I am going to share some simple trick with you. So with that trick also, you would be able to quickly remember. Okay, so across the period, when we are moving from left to right, ionization energy is increasing. So this means that slowly and gradually ionization energy values would be more and more for these elements. Okay, so highest ionization energy would be for these elements. Okay, 10 and 18 highest, and we know these elements are 10 and 18. It is neon, it is argon. Now our question is least ionization energy, which would be having least. So come back again, the ionization energy would increase, right, from this element number 3 to element number 10. So least would be, yes, element number 3. And similarly in the same case, the ionization energy least, it would be least for element number 11. So the least ionization energy are shown by A and I. We got our answer. Okay, now have most non-metallic character in the period 2. Non-metallic character in period 2. Now we have to focus on this period, just 3 to 10. Now we know non-metallic character increases across the period. How to quickly remember this? I have already told you. Here there are metals, here there are non-metals. So non-metals here, if they are present, non-metallic character here is more. It would be less here, from less to more, which means it is increasing. So non-metallic character is increasing when we move across the period. So here it would be more, right? The highest non-metallic character would be here, and it would be shown by this element. Okay, 9, not 10. Okay, don't get confused or don't get wrong here, because the 10 is neon, atomic number 10 is neon, and we know that neon is having very stable electronic configuration. It won't show non-metallic character. Okay, it is very happy with its own electrons. So highest non-metallic character is shown by fluorine. Okay, 9. So our answer is G. So with this we have reached the end of this video, and I hope you have enjoyed learning with me. I truly enjoyed teaching you. So Please do let me know whether you have understood whatever concepts we have learned so far and you enjoyed enjoyed learning with me or not in the comment section. Rest concepts of this chapter we would be seeing in the next video. Till then, see you, stay tuned and have a great day.